xi minus 1 and take sum. This is your LF principle.
Yes.
And this piece. Difficult to prove. Okay. Or like to write with proposition. Another proposition. Let's suppose F is a map of B and it is bounded and let's want it to be what? Any two partition. Any two partition. They may not have relationship between partitions of A comma B. Any two partition. One is not necessarily refinement of other. Okay. Then this is true in general actually. Unless P1 is less than or equal to in other words, no matter what partition you take, it's like it's a generalization of this result because here you have a same partition while here you have any partition actually. You know, this is something very interesting actually. Just think about it. Take any two partitions, lower Riemann sum, and just think about it. You know, this could contain huge number of points as well. Well, this could contain small number of points. But still this number is going to be bigger than or equal to lower Riemann sum. And proof is pretty much simple. Just one-liner proof. Consider partition P, which is a refinement of. Okay. What is the relationship between LFP1 and LFP actually?
Lessons.
So less than or equal. Why? Because that's a common refinement of CP1 actually. How about the relationship of LFP with UFP?
Yes.
Well, and how about the relationship of UFP with UFP2? So P1 union P2 is a refinement of P2, and we just saw that if you have refinement as a lower upper sum, then
Yes.
okay, simple. Now we have defined some of concrete things. As I said, that for an interval you can have lots of partitions, but which partition is going to give you the better approximation of area? That partition. For which, you know, you have a supremum of lower Riemann sum, maximum of upper Riemann sum. Definitely. Yes, that's good. will prove next that if they agree with each other, that the exact area of the and that equality or that number basically you call that as the parallel of
Then,
F. It's very much intuitive. Suppose F is bounded, so you need to keep this thing in head. This theory is only true for bounded functions. Okay. If the functions are unbounded, have other case too. So suppose F is bounded. Okay. Now I'm defining lower integral. Lower integral, I'll put the bar basically. Lower integral F. This is what? This is that you take the LFP over P is the partition of A to B. Okay. So this set is what? This set is set of all lower sums. Okay. That you can make through any partition P of the interval A to B. Okay. And take their supreme. See that which is giving you, which partition is giving you the maximum value of LFP. Okay, and whatever this value is going to contain. Question, why this supremum should exist? Because the function is bounded up. So we can say that these LFPs are going to be bounded. So that's a bounded set. Hence, the supremum should exist. Whenever I just write a supremum with something, you should ask question that can we find supremum? Previously, we were able to find supremums for each sum interval because they were bounded as well. The function was bounded on both sum intervals as well. Anyways, we can make it more precise, but I'm not getting into it. So, these guys exist actually. No doubt about it. Yes. And how about, okay, so we name this integral as the lower Riemann integral. Okay. It's a lower Riemann integral. Some people call it lower integral. How about AP and upper F? What do you think? What it should be? It should be the infimum of UFP. Try to make UFP smaller as much as possible. Use partition of AB. Define, and obviously this should also exist. There's no doubt about that. Like, we prove a proposition. What do you think? Which of these numbers should be bigger?
maybe
Others, if I have upper
greater than
that's what the competition is. Okay. So we are going to proof. That E partition of HP yes. Then for any other partition Q for LFT, what should be the relationship between LFP and LFQ and UFP? Should be smaller than or equal to this. So just think about it. This UFP is like upper bounds for LFQ value. So no matter what Q you take, could be P, could be bigger than P, smaller than P, doesn't matter. So LFP, LFQ is less than or equal to UFP. Like UFP, this fixed UFP is kind of upper bound for all of these lower Riemann subsets. So if it is upper bound, you take the supremum of all these upper bounds. What should be the relationship between that supremum and this? UFP.
Same.
So supremum is what? Just think about it. So I'm taking supremum of LFP where P is any partition. Supremum is taking over the partitions. Okay. For every partition, you have an LFP and you are taking the supremum. My question is, from this we know that UFP is upper bound, and we also know that this is also upper bound basically.
P is fixed.
Huh?
P is fixed.
Okay. Sure. Take over Q. Agree? Which is basically what? A to B. That's like something very elementary. So for LFQs, I have two bounds. One is a generic bound, and other is this least upper bound. Question: what should be the relationship between least upper bound and this upper bound?
Less than or equal to.
The least upper bound is smallest of all upper bounds. So if there is another upper bound, it should be smaller than or equal to your least upper bounds. It's just simple application of definition actually. Okay? It's nothing. Okay. All this equation number one. Okay. But what is going to be the relationship between now let us think about it. F less than or equal to P is any arbitrary partition. It's an arbitrary partition.
Obviously.
Now, this fixed number is less than or equal to any of UFP. So what should be the relationship between this number and the infimum of UFPs?
Always same. Less than. It will always overestimate.
So what does this shows? This shows that this guy is a lower bound for UFP,
Yes.
while this guy A to B bar F is the greatest lower bound. So all other lower bounds are smaller than this actually. Just think about it. Okay? By definition. There is nothing, it's just a good practice of supremums and infimums. So this implies that this lower Riemann integral is lower bound, like the lower bound what? For P, where P is partition of AB. Okay. P is partition of AB. It's a lower bound for this set. So if it is a lower bound for this set, then this lower bound must be smaller than or equal to the greatest lower bound, which is infimum. Okay. Which is infimum. What is the definition of infimum? So it's like the greatest of all lower bounds. Okay. So this implies that this guy A to B F should be less than or equal to the infimum of this set. F P and then P is a partition of B, and which is equal to upper Riemann integral. It's tricky, but just you're making sense. Yes. Now I like to define Riemann integral. Form to E into R is bounded say that F is integrable if something as per as our expectations happen, that this lower integral, lower Riemann integral, which is infimum of, which is supremum of all LFPs, should be equal to what? lower Riemann integral and upper Riemann integral, and if they turn out to be equal, then you say that your f is integrable. And if it is integrable, the question is, what would be the integral of it? The integral of basically f, general integral of f is going to be this shared value. So they must be equal to something. So that something is the integral. That is, let's say, EF. Okay. It's equal to what is this shared value? Okay. Let's compute the integral of the function. Next example that I'm going to. So there are lots of limitations of this definition, this way of defining integrals. And one of the limitations you're going to see now in this example. And there was a reason, or such kind of functions were the reason that a new theory of integration was introduced, which is what you call measure theory, that measure theory. If some of you will be interested, you can take that optional course. Okay? I'm going to be so it's optional. It's optional course. So if you, not necessary for you. So it's elective. And if you wish, you can take it. If you don't wish, you can take something else.
Pure science.
Uh-huh.
Is it pure science? Sir?
So it's going to be pure science.
What is such a medicine?
So it's going to be advanced analysis. There you will see that those functions which you can't, so there are loads of functions which you can't integrate by this definition. Here is one of the example. So the question is, can we do something in such a way that we can define integrals for those functions as well? And the answer is yes, actually. And if you want to know, wait for the measure theory. Okay. There is going to be theory of integration, general. Very powerful. So consider a function f. So it's like a crazy function f. So f of x is 1 when x is rational and it's 0 when x is not rational. A certain function. First, can we integrate it by this definition? Okay. The answer is yes. Then take any partition P, okay, or then what would be the LFP for this function?
Is sum of
What would be the LFP
sum of sir.
for this partition? Huh?
Sum of summation sir.
So obviously it's going to be sum. Sum of what?
Exactly. F of x sir.
Y, xi,
Exactly.
so that's xi and so on. Okay. What should be the MR for this function? So infimum is just take two values, so infimum and supreme, for 0 and 1. So infimum is also going to be between these two values. infimum is supremum of 0, 0 times xi is xi minus 1. No matter what partition you choose.
Because we do
If LFP is 0 for any partition, how about lower integral, which is supremums is LFPs? So what would be that? This. 0 as well. Okay. If you take any partition, if you LFP, you get 0, so the supremum must be 0 as well. Okay. How about UFP?
Submission.
It's going to be summation
one time.
1 times xi minus xi minus 1. Is that what is the supreme or method? It's going to be 1. If this is the case, then the integral is going to be going to be b minus a, like endpoints. Everything is going to cancel out except endpoints. I was from like one end. And how about per integral f is going to be what? What do you mean by? Sorry. Okay. Alright, so we should explicitly mention that f is only defined on 0 to 1 actually. Okay. The endpoints are 0 to 1, so it's going to be 0, which is equal to 1. But f was defined on a to b, it was also a. So what would be the infimum of UFP? So it's going to be 1. So lower integral is 0 and upper integral is 1. So both are not equal. So by this definition, f is not integral. Not defining the integral. Okay? And that's which kind of led Lebesgue crazy actually. Wow, my definition not working. What we need to do, we need to modify our definition, which are not going to do now. So it's not Riemann integrable. We're going to see that we can define basically integral for such kind of crazy functions. Right? Okay. Now, the part that so far I have covered is basically from Rudin, okay? And it's also on Rudin, but it's Rudin on one page. Rudin is not getting into the details of Riemann integrals, but he is interested in generalization of Riemann integrals, which is Riemann-Stieltjes integral. Okay. So here you are, roughly this integral is like integral of f with respect to dx actually. Like you are just taking what, this difference, xi minus xi minus, but just taking the length actually. But we can actually generalize these results. Okay? And define Riemann-Stieltjes integral. So I'd like to end discussion on defining Riemann-Stieltjes integral. Okay? And mentioning the similar properties. So from the next discussion, we will prove all of our results with respect to the Riemann-Stieltjes integral. So these are going to be true for Riemann integrals as well, because Riemann-Stieltjes integral is generalization of Riemann integral. Okay, Slodden only deals with Riemann integrals. It doesn't deal with Stieltjes integral. While we would like to prove things for Stieltjes integrals. Okay, I didn't directly jump the way Rudin has jumped into Stieltjes integral, so I just kind of gave you a quick overview of what Riemann integrals are. Now like define what are Stilge's integral and some of the basic results. I'll not prove those, but they are proof really are analog of what you have done here. Okay, but just mention it and end discussion and